Okay, so we're on to P4 now, which is waves. Remember in the last video I talked about energy being transferred in the form of waves, whether that be sound waves or light waves. So essentially you can get information or energy being transferred without the actual matter moving from two points. So an example would be, obviously, if a teacher is talking to you, the air particles in front of his mouth are different air particles to the air particles in front of your ears, but yet you still hear the sound information being passed on to you. Okay, and same thing for this example here. If you drop something into a pool of water, okay, you're obviously going to see the wave motion across the water. But if you dip a ruler into one point of the pool, the individual water particles are just going to go up and then down. Okay, they're not going to move across. Okay, I'm going to define several key terms. One of them is the frequency, so this is the number of waves per second. So if I look at this transverse wave here, I'm going to define it in a second, but basically it's the amount of waves passing a point per second. Okay, the wavelength is the distance between two consecutive points of a wave, so it could be from this peak to this peak or this trough to this trough. The amplitude is the distance from the rest position or equilibrium position of the wave, so it's going to be from this point to this peak or this point to the trough. Okay, the time period is how long for one wave to pass a point. The wave speed is obviously how long the average speed of the wave is. Wavefront is essentially the front of a wave. Okay, so we're going to look at what a transverse wave is. So the way I tell students is, if you think about a transatlantic flight where the aeroplane goes across the ocean, think about the sign a cross makes. Okay, so it's 90 degrees between both lines, which is what perpendicular means. So that means the vibrations are going to be perpendicular to the direction of travel. Okay, examples of transverse waves are obviously electromagnetic waves, which light waves are included into that, water waves or Mexican waves. Longitudinal waves, on the other hand, the vibrations travel along the direction of travel. That's how you can remember it, along and longitudinal. Okay. Examples of longitudinal waves are sound waves and ultrasound waves. Okay. And infrasound waves as well, and we're going to be looking at the difference between them in a second. Remember I said that the keywords of velocity or the wave speed, the frequency and the wavelength will be linked to an equation. Well, this is the equation, so the wave speed is equal to the frequency of the wave times the wavelength. Okay, please note the units for frequency are hertz, okay, denoted here by capital H and lowercase z. Okay, we've seen this equation before. We can also work out the speed of a wave if we know the distance one wave front covers and the time it takes to cover that. Okay. So, simple way to measure the speed of a wave. Got a tape measure. You got a stopwatch. Okay. You know, start the time when you see the firework and stop it when you hear the sound. Okay. And this is for sound waves, because we know that the sound will be emitted when you see the light, when the firework sparks, and obviously the time it takes for that sound wave to reach your ears is going to be the time. Okay, and if we know it's 300 meters away, we can work out the speed. Right, now we're going to look at refraction now. Okay, so if we've got a light ray traveling into a glass block, in fact, first of all, I'm going to talk about this one here on the right, okay? The way I tell students to know how to draw refraction diagrams or these ray diagrams is to imagine the light ray as a series of parallel lines, horizontal parallel lines, okay? Kind of like a rail track. So if you imagine this light ray, okay, it's got a horizontal width. It will stop, okay, immediately here at the boundary of the air to the glass, okay, and then it will immediately slow down the entire horizontal length, and it will go slow, inside the glass block, and then the entire width of that light ray is then going to speed up. So we've got no angle whatsoever, we've got no change in direction. So if the light ray is coming in at an angle like this, let's imagine our railway track, okay, got a series of horizontal lines. This end, okay, of the of our width of our light ray is going to reach the glass block first, so it's actually going to slow down, okay, whereas this length is still traveling in the air, so it's still going to go at the same pace. And if you imagine sort of like a ruler, okay, traveling at an angle towards this glass block, this end is going to slow down, and it's actually going to cause this entire light ray to bend inwards, okay? So if you imagine this side slows down first, okay, kind of like a car curving around a bend, okay, it's actually going to spin this way, okay? So the light ray is actually going to travel or move towards the normal, okay? And the normal is an artificial line, it's just an imaginary line that is drawn 90 degrees to the surface where the light ray hits it, okay, or leaves it. So it's refracted inwards. Let's do the same principle. So our horizontal railway tracks, okay, are going along like this. This end is going to reach the air first, so it's actually going to speed up. So we're actually going to, this part of the wave is going to speed up, okay, whereas this part is still going to travel slow, so we're actually going to bend this way away from the normal here, okay, so that's why the angle increases. One important thing to note down, this original incident ray is going to be parallel with this refracted ray here, okay, and if you're doing this experiment, obviously you can draw some dots here, okay, the dot here, a dot here, a dot there, and then you can join up the dots, and then you can join, or when you remove the glass block, you can then join up this dot to work out the refracted ray inside the glass block, okay? So you've got these sentences here to help you remember that, if that's going to be useful for you. Right, it says, which scientific words best describe the following? When waves reach a different material, they can lose some of their energy to the material they enter. So that means it's going to be absorbed. When they pass through the material, good scientific word for that is transmitted. When they bend through the material is refract. When they bounce off the material is they reflect. Okay, so make sure we put these correct scientific words in our answers and we understand what they mean, okay? So obviously these are 4 different things that waves can do when they reach the boundaries of different materials. So we're going to talk about infrasound and ultrasound now. So ultrasound is any frequency above 20,000 Hertz. Infrasound is any frequency below 20 Hertz. So humans have a range of 20 Hertz to 20,000 Hertz approximately. Sounds are created, in fact, let me talk about some uses of ultrasound. Ultrasound can be used to eliminate or destroy kidney stones due to the high frequency, and it's got to be a focused beam of ultrasound. They can also detect fetuses inside the mother's womb, okay, give a clear image of them. Infrasound can be used to detect seismic waves, and also can be used to detect the internal structure of the earth. Specific animals such as elephants and whales can communicate also using infrasounds. Right, another common exam question is examiners like to ask you about how a sound wave is produced. All you need to say is the voice box or the loudspeaker's diaphragm vibrates back and forth, okay, causing compressions in neighboring air particles, which then pass on those compressions to further neighboring air particles until they reach the eardrum of the person listening, okay? And you just need to mention that the vibrations are parallel or along the direction of travel, which means it's a longitudinal wave, okay? So again, don't need to worry too much about the biology, but eventually the vibrations will hit the eardrum, and those vibrations are caused initially by the initial vibrations from the voice box or the diaphragm of the loudspeaker. Right, we're now going to talk about ultrasound and a specific use of it called sonar. So sonar is a way for ships and submarines can measure depths or their local surroundings. Essentially, you need to be careful, and a lot of students miss out on this, is to multiply the distance, also, sorry, to half the distance. So if it takes 0.02 seconds to return from when it's been reflected from the deep surface below, it means that it took 0.01 seconds approximately to reach that surface. Okay, so that's why when we've worked out the distance here, when we've rearranged speed equals distance over time, we've used the speed of 1500 meters per second times 0.01 seconds instead of 0.02 seconds. Okay, so please bear that in mind. The time it takes for the signal to reflect and come back to the boat is obviously twice the time it takes, and the time to reach the bottom has got to be half of it. Okay, so we're now going to talk about prenatal scanning, which is obviously one use for ultrasound waves, essentially similar to how sonar works. Okay, ultrasound waves are sent into the woman's womb. Okay, whenever they reach a new material, some of it reflects back, and then the handheld scanner detects the time taken to return and builds up an image from the respective times. Okay, now this is all done onto a computer. Okay, so similar to sonar on the submarine up here. Okay, the computer can create an image depending on the respective times for the signal to return to the detector. Okay. Finally, we're just going to talk about infrasound and its use in detecting the Earth's structure. Okay, there are two types of infrasound waves. Okay, that you need to be aware of. Okay, S waves are transverse waves and can travel through solids. Okay, so obviously, if there's liquids present, we will not receive a transverse signal, okay, from a particular point, and we will know that liquid's present as a result. P waves are longitudinal and can travel in both solids and liquids as well. Right, also please note down as well that P waves are generally faster than S waves, and also if S waves don't travel through liquids, there's going to be regions where you're going to have no S waves being shown, which means the core has got to be liquid. Also, due to refraction, okay, of the different layers underneath the Earth, you're also going to get sections or regions where you'll get no P waves being detected, okay, as shown here. Okay, and finally, just to end this unit, when sound waves travel from one material to another which is harder for sound to pass through, the following changes happen. So, speed decreases, but frequency remains unchanged, and wavelength decreases. When sound waves travel from one material to another which is easier for sound waves to pass through, these things happen. So the speed increases, the frequency remains unchanged, and the wavelength increases. So please remember these things. So the frequency remains unchanged, but the speed and the wavelength decreases. Okay? And that ends this video.